Salvation models and excited states, a hopefully helpful guide. What this is an attempt for me to find a linear path through the fun mind map of this field for my IPR, and also an opportunity to see how much I understand by trying to teach it all to you guys. I'm going to be trying to conceptually explain the theory mostly, but have a few orange recommendation slides for your too long didn't listen moments. This is probably going to be an in-depth explainer in parts, and those are the parts that I've needed to put a lot more work into understanding, so I figure that you'll probably want a bit more depth in me explaining it. A disclaimer for people online, I'm only just starting my PhD and this field is an absolute mess. It's poorly documented, inconsistently implemented, often black box without specifications, and assumes you just know already. Most of the proofs and explanations are given in some of the heaviest maths imaginable, and it's taken me a solid 8 months to get to where I am. I chose to make this presentation because I wish I had a resource like this, and making these slides has reminded me of how little I truly understand. These have not been fact-checked by a higher authority, so do not hold me responsible and do not at me, please. So, I'm going to speed over the undergrad level basics and focus on the more interesting minutiae instead, but we'll start with solvation models. So obviously, explicit solvation is important. Cluster solvation only models one structure though, so that's when we have our solute surrounded by solvent molecules. So MD sampling is required, which means that you need to take a lot of different structures in order to be able to get an accurate representation of what's going on in the solvent. This problem also lacks long-range electrostatics when using a small solvation shell, so you do need to add a lot of solvent molecules, so it gets very expensive if you don't do that. Multi-level approaches do exist, however, they tend to lack mutual polarization unless you start using like EFPs and things like that. So if you're doing onion, then you're literally just calculating the inner level energy and the outer level energy and subtracting them, so they're not interacting per se. Density embedding is a really cool method that I have seen a few people use, but it requires QM calculations for the solvent region. It's just another way to do onion style calculations. And there's, yeah, but there's no analytical gradients implemented in most of those approaches. The important thing to take away here is that energy and properties are solvent structure dependent. So this approach is kind of very limited in general, just because you do need to sample a bunch of different structures to get anything reasonable. And this is all I'll say about explicit solvation. So implicit solvation, PCM breaks down into a few different terms, which the undergrad models describe something like this, where you have electrostatics, cavitation, dispersion, repulsion, solvent structure, and charge transfer. We know that these non-electrostatic terms overlap a lot. Everything is electrostatics, right? So describing the non-electrostatic terms separately is a bit redundant, but we'll come back to these terms later. Starting with electrostatic terms, though, these are quite simple. We put the solute in a cavity and describe the bulk, we put the solute in a cavity with a dielectric bulk on the outside, and we allow the solute and solvent to polarize each other within the SCRF cycles. So cavity with a dielectric on the inside and the outside, charge appears on the inside, say from our solute, polarizes the outside, and then they can polarize each other respectively. Older approaches to this use spherical cavities and solved equations analytically. Newer methods involve discretized cavities, and we'll get into that here because cavity generation is kind of fundamental to anything that you're dealing with on this front. So van der Waals surfaces are one way to do it. So you can see the inner gray line, and this is literally just what is the radius of the atom. Let's sum them all together and create a big shape of it. The solvent excluded surface, you can sort of just see it here. It's this blue line here. So up here, this little thing here, where you have your van der Waals surface, but then you've got some sort of thing that tells you, you essentially run a probe along the surface to see what can the solvent actually get to on that molecule. This is also known as the Connolly surface. The solvent accessible surface is essentially your van der Waals spheres plus a certain radius. And this is often the solvent probe radius, and usually instead of having an explicit solvent probe radius, you'll just scale everything by 1.2 times. And this may include or exclude protons. So there's the unified atom model, I think it is, and it essentially excludes protons, and in some situations that is a better option. Choice of radii, all of these radii are derived from parameterization. So these have the largest effect on the electrostatic term and can act as a scaling factor. And a lot of people use this to overcount electrostatics to ignore other terms. These are some options. You'll probably recognize some of these from different force fields. My recommendations on this is use whichever the rest of your model is parameterized for, is the simplest bit. These are often used to overscale electrostatics to cover up for a lack of non-electrostatic terms, so be wary of this. We'll come back to SMD because it uses its own scaling factors. But once you've got this cavity, you need to actually discretize it in some way. So to take the points of that surface and make it into a surface that you can run calculations on. So you need to place point charges along the surface to be able to do your electrostatic calculations. So isodensity is the simplest in concept and the most chemically and physically accurate, but is non-continuous across the potential energy surface and doesn't have analytical gradients, so it's not really used or spoken about much, but it is a good option if you do want to do any single point calculations, assuming that your model is parameterized for it. Tesserae methods are probably the most commonly implemented, and these build a surface by using conjoined polyhedra, as you can see on this. I think the projectors at the back are a little more stable if this one's giving you a seizure. The area of the tesserae surfaces, the tesserae faces themselves are used to weight the point charges that are produced, and each vertex is used as the location for a point charge. The potential energy surface produced by this method are not continuous though. And we can see that because when we start to build our cavity, we start with our surface, we put in the polyhedra on top of that, and we put in our point charges. But as we start to scale the geometry, we have two big issues that pop up. The first is that points disappear as they get consumed by the molecule itself. And the other problem is that as these points approach, you end up getting Coulombic spikes. The second point can be fixed with Gaussian blurring of the charges, so that's not too bad. But the other point is a bit more tricky. And so what we've done in a lot of methods is implemented switching functions, which are these purple lines here. And they essentially say that at that intersection, rather than just getting rid of the point charges, we're going to take them and scale them down depending on how far into the molecule they are. So they still exist, they're just kind of switching smoothly between the polyhedra. Another method that has become very popular and is sort of a very good method is called SWIG, and this starts with Lebedev discretization. So we start with our cavity as we did before, but now we use Lebedev discretization since it's, Lebedev quadrature, since it's can be systematically improved, so you can just increase the numbers and get better results. The charges are Gaussian blurred, and there are switching functions inherently implemented in this model. The other thing this does is that it puts these toroidal intersecting, toroidal re-entrant surfaces over the top of those switching functions to make it more continuous. And we can sort of see that in this graphic here, where the black points are all generated from the Lebedev discretization, blue is toroidal, and orange is switching. So my recommendations for this are essentially, isodensity is fantastic, but doesn't have gradients and thus isn't implemented much. These overcome outlying charge issues, which we'll talk about later, because the charge is, you're choosing the cavity based on the extent of the electron density as opposed to just hoping that the electron density sits within your cavity. SWIG is the gold standard at the moment, but it's only implemented in a few programs, namely Orca and QChem were the only main ones that I could see. I don't even think Gaussian has it, but don't hold me to that. Switching functions are always a good idea for optimization and can reduce SEF convergence issues. Optimizations in particular, you can get massive spikes in your potential energy surface that can completely throw off your geometry if you're not using some kind of switching function. And if GPOL is all you've got, then your software probably doesn't really care about solvation, so maybe try something else. Sorry, Sci4. Yeah. There are a few external packages. I like PySCF is another one in that regard. Like it only has DD Cosmo, which is not terrible, but it has the same sort of issues. It's great if all you need is single point electrostatics, but that's it. For actually calculating the PCM, we have a few different formalisms, and this is where I'll start to get into a bit of the maths, but this is how we sort of calculate the actual energy from the charges that we get on our surface. So the first one is the most simple, and this is generalized Born. This is essentially an analytical solution to the Poisson equation where we use point charges. So this is used in a few methods, but it requires a spherical cavity with all of the charge to exist inside of that cavity, which is not the most reasonable thing to ask for QM calculations. But the Minnesota models do use this, but they use this in conjunction with a charge model itself. So they calculate the charges based on empirical factors and they put those in a cavity. And so they use that. Everything is parameterized, in other words. Yeah, so that's all I've put. Onsanger took this further and said, let's do generalized Born but with dipoles, which is still not that much more useful for QM. And Kirkwood took this to multipoles, so that's kind of cool. We get into the non-analytical methods, though.
It's kind of exercising in
Yeah. This will fix all the problems, right? I mean, admittedly, there are some methods for larger scale calculations where you can treat distant regions with multipoles, but I won't get into that. We get into the big, heavy lifting one here, though, which is CPCM, or the conductor-like polarizable continuum model. So this solves the SCF equations for epsilon equals infinity, so a conductor, and then it scales those for epsilon equals epsilon 0, which is the epsilon of your dielectric constant of your solvent. In this equation, this is kind of the important one here, which is the scaling factor. Sigma S are the resulting charges from our solute, so this convention will be used throughout this presentation. Psi 5S is the electrostatic potential of this solution from the Schrodinger equation, so that's what we're scaling everything by, and F of epsilon gives us this function here, which is our scaling factor, and in this case for CPCM we use 0 for zeta. This is different in Cosmo. Also, yeah, please don't make me go through the precursor equations to this because it's some heavy calculus. Cosmo is the next step to this, and it's very similar to CPCM, but works using zeta equals 0.5. The true form of Cosmo, described by Plant and Jonas, has a double cavity though, and this is to make sure that we're not missing any charge. So we use the solvent excluded surface, which is the smooth van der Waals, for the main screening charges, and then we have the solvent excluded surface plus the solvent probe radii times 0.95 for the outer cavity. And this is used to capture any outlying charge. But be wary that if you see Cosmo in a package, it's probably just CPCM with zeta equals 0.5. Very few packages implemented with the double cavity. IFPCM is where we start to get into the better solutions. So this is the integral equation formalism. This is where I really can't explain the maths all that well, but this is an exact reformulation of the classical continuum electrostatics problem, assuming that all the solute charge is contained within the cavity. That's a big assumption. For QM solvents, there's always going to be escape charge for realistic cavities. So SSVP takes this and corrects IEF-PCM by reformulating the equations to assume that there is going to be a certain amount of outlying charge. We know that, and assumes that the dielectric boundary electrostatic potential is going to be accompanied by a volume polarization arising from this outlying charge. So a second surface charge must therefore exist that balances out the volume polarization. My recommendations here are obviously don't use generalized Born, Onsanger, or Kirkwood. They're obsolete unless your whole model is parameterized around them, and that is definitely going to be a parameterized model. CPC and Cosmo are pretty much equivalent and are both good for high dielectric solvents, so anything above 10, they're pretty good. These will be equivalent to IFPCM as your dielectric gets bigger. IFPCM is generally better than SSVPE when van der Waals cavities are used. They behave almost identically for isodensity cavities, which is why if you do have a choice for isodensity cavities and you're just in single points, you may as well consider it. And they're almost identical when emitting protons from the cavity generation, the unified atom model. So would you be able to close the door? Sorry. Always use IF, PCM, or SSVP for low dielectric solvents, though. But now we get into the fun bit because we have the non-electrostatic terms. And this solves for the other terms like cavitation, dispersion, Pauli repulsion, hydrogen bonding. And all models are parameterized to some extent in this domain, either by making specific models from bespoke datasets or based on molecular mechanics force field. Complexities, everything is electrostatics. So the different terms are very intertwined. Hydrogen bonding is a part of electrostatics. Dispersion and repulsion are very intertwined and highly dependent on the cavity generation itself. The cavity largely stems from non-electrostatic repulsion, yet the cavity is fundamental to the electrostatic term, and all the properties, including the PCM cavity, are solvent dependent. So it requires us to treat everything in unison. Everything must be parameterized together. This is really important. You can't just pick and choose different components from different methods. Smush them together and hope that you're going to get a good result. Molecular mechanics-based dispersion repulsion is sort of not a great model, but it's one that we have, and it typically uses Lennard-Jones or Buckingham parameters to calculate the dispersion repulsion term. These are very force field dependent and require the solute to be explicitly parameterized, which we know that doing any kind of intermolecular parameterization for molecular mechanics is dodgy at best, and quite often not manually, not specifically parameterized, just quite often just generally taken from a table somewhere. So these are not a good approach and are fickle to use. Wouldn't suggest them even though they are implemented in QChem. SARSA-based models, or solvent accessible surface area, these are sort of a really good approach where the properties are dependent on how much of the molecule is exposed, and you have different properties for each atom. So you integrate over the exposed surface of each atom and use atom-specific parameters to define the non-electrostatic terms. For some reason, Kramer and co. use sigma to define these as well, which is really frustrating. Too many sigmas in PCM. The most known successful SARSA approaches are the solvent model X approaches from Minnesota. So these are Tramer, Kruller, and co. So if you think SMD, SM8, SM12, anything like that. The numerical SM methods, as I said before, use the generalized Born cavity, and they're parameterized using charge models that they call CMX, for charge model number. So creative, I know. All use the SARSA approach to calculate cavitation dispersion structure as a single concept, so the CDS term, and they're very transferable to new solvents because all you need are the physical parameters of those solvents, the physical properties of them. And they're very accurate for species that are within the Minnesota training dataset, which is mostly organic species. So it's actually very elegantly simple maths. As we can see here, it's literally just a sum of all of your solvent parameters by some kind of scaling factor that gives you these these terms. So here we can see, and this will pop up a lot, epsilon for the dielectric, n squared, which is the refractive index squared. This is also considered the optical dielectric constant, and this will come up a lot when we get into excited states. Abraham's hydrogen bonding acidity and hydrogen bonding basicity. These are, again, physical properties that we can calculate and measure. Macroscopic surface tension, again, physical properties, and fraction of the solvent atoms that are aromatic and that are electronegative halogens. And these are obviously things that you can count on your hand. So
basically,
yeah, it's very simple.
like if you think about it, they say, what do? You just throw all the parameters together, all the parameters know about the molecule, and for closures, and then they just
Yeah. So very simple, very transferable as a result, and there's a reason this is kind of considered one of the best models that we can use at the moment. Typically, it uses an IF PCM with van der Waals radii for the core, but now people are starting to use CPCM for high dielectric solvents, which I kind of say stick with IF PCM if you're going to use SMD. One thing to note is that it uses different radii for the solvent accessible surface area as it does for the electrostatics. You can't use the same radii for them. Non-electrostatic terms are weighted sums of these linear combinations according to the SASA, as I said before. Physical methods are different approaches. These attempt to be more physically rigorous than SMX models or SASA approaches. And these usually calculate dispersion and repulsion from frequency-dependent polarizability of the solute and converts it into a C6 coefficient. Yeah, firing off some physicsy buzzwords here. You can tell that this is where I start to lose interest because these are not the most useful methods in a lot of respects. Cavitation usually comes from scaled particle theory, solvation energies. You can also use VV10 dispersion with a bulk solvent density if you want, but this requires integration of the volume, not just the surface area, so it becomes quite expensive. Repulsion from interpenetration of non-bonded densities. Again, lots of physicsy, boring stuff here. This has all been implemented in CMARES, which contains 5 empirical parameters for a solvent, which have only been calculated realistically for these few solvents, so not the most useful. It uses an isodensity SSVPE formalism and is more accurate than SMD, but it is a black box implementation and it's only available in a couple of packages, and it's obviously only for single points as well, so not the most useful thing. Another black box approach is the Cosmo RS approach. We really don't know a huge amount about it. It's proprietary and only works within Cosmotherm with input files generated from other QM packages. It is completely closed black box, so I'm not even going to bother looking into it really. My recommendations are actually pretty simple, and it's a hierarchy. SMD is pretty much the best for speed and is implemented in Orca Gaussian games, QChem, etc. Not Sci4, not PySCF. Always choose SMD if you have the choice. M-based models, don't touch them. CMARES is better than SMD, but doesn't have gradients, and I've only seen it in games and QChem, if you really want to use games. Cosmo RS, really only good for industrial applications, bulk screening, that sort of stuff, where you want accurate predictions and you don't care how you got there. I haven't spoken about RISM models because these are only implemented in ADF and the literature doesn't really care about them anyway. So this is where it kind of gets tricky because we have to think about solvation in terms of correlation as well. And so the tricky bit is, when do you apply the solvation? Correlated methods become quite expensive. And if you think about what we do with the SCF, where we're iterating back and forth, we're making it self-consistent to some point. And that is self-consistent within that SCF procedure, which in most cases in non-correlated methods includes pretty much everything that we need to consider. In correlated methods instead, we have these 4 approaches really. There's technically one more that'll pop up a bit later, but these are where you apply them. So in PTE, you're doing non-correlated solvation, and then you're applying your correlation as a correction to that. In PTD, you're kind of doing everything in gas phase, and then you're applying solvation. In PTE, PTD, you're doing both. So you're doing ground state in solvent, doing correlation, and then reapplying solvent with your correlated wave function. And then in PTED, this is where it gets really expensive, where you're iterating over the whole SCF procedure, correlated procedure, solvation, and then back to the SCF until everything is self-consistent. So very, very expensive to go that way, but this is implemented in a few packages. I know Gaussian uses this, for example. We will come back to these terminology a bit. Summary for ground state. The only big thing here to take away is that there isn't a huge amount of consistency between packages and implementations, and not all implementations are made equal. It's extremely easy to get good results through overcounting one term to account for not including another. So you'll see this a lot with electrostatics, and any method that doesn't have non-electrostatic terms is incomplete. These terms cannot be mixed and matched. I can't stress this enough, because if you just choose a CPCM model, you're not handling solvation, you're just handling solvation electrostatics. Always choose SMD if you have the choice in whatever package you're using. Pretty simple. Gaussian isn't specific about which terms it includes and seems to include non-electrostatic terms in CPCM calculations without specifying, and reading through their documentation, they really don't say much about where these come from. So I don't trust it. When in doubt for the ground state, this is my hierarchy. it's recorded and I'll upload these slides, so I'm not going to go through it all. Not recommended, but functional. PyCF uses GPol.DD Cosmo, scales better than Cosmo, but it has no electrostatic terms, and Sci4 does have GPol plus CPCM. It's not great. Numerical gradients only, not necessarily worth using. And I need to put this slide in because I am quite biased. I don't care about getting exact solvation energies, though this may change later in my PhD, apparently. I don't see a method without analytical gradients as being practical, to be perfectly frank. If you can't optimize it, then what's the point? Like, you're just using bad geometries to get good energies? That's silly. And methods that require any kind of external software or black box approaches are cumbersome and unscientific. So just great for industry in the same way that machine learning is great for industry, not so great if you want to understand the intricacies of what's going on. So, solvation models for excited states, it's going to get bumpy here. This is where things start to get a bit more complex. There are two main methods for calculating excited states in QM. I kind of have to touch on this, sorry. Linear response theory is used for perturbing the ground state wave function, and equations of motion is mostly implemented in correlated methods. I don't really know a huge amount about EOM, and to be honest, I probably won't explore this just because they are so expensive. I mean, when you start doing CCSD calculations and then you need to do an extra step on top of that and optimize within that space and then apply PCM, it's just not worth it. I might come back to these in PTX notation later. There are a few slides on that. But this is sort of the general gist of it for anyone that does really care. Essentially, what we're doing is we're taking our ground state wave function and then we are perturbing it, and we're using, it's an eigenvalue problem. So it can solve itself consistently, and we can diagonalize it for limited roots using a Davidson method. So you might want to only like the first 4 roots, as opposed to diagonalizing and getting every single eigenvalue, which could be ridiculously expensive. So there are ways to get cheaper calculations, and the fewer roots you solve for, the less time your calculation will cost. And yes, Carter, I did borrow this from Lars's talk on Friday. A and B rely on converged ground state orbitals and the exchange correlation kernel. So this is quite specific to DFT, though there are linear response formalisms for non-DFT methods. And if we ignore B, then we get the Tam-Dankoff approximation, which I will touch on, I think, at the very end. So, this is where we start to get into PES territory. Let's start with 2 states, our ground state and our excited state. Here we can show the energy of the ground state at the ground state geometry and the excited state, as well as the energy of the excited state at the ground state and excited state geometry. So the important thing is here that we have 2 sets of geometries. The equilibrium geometry for the ground state and the excited state are different, and you can have the energy for both states in both geometry configurations and technically anything in between. This also goes for higher roots as well. There's going to be a difference between the equilibrium geometry for each of the states. When we do a vertical transition, we're solving for more solutions to the Schrödinger equation from the current geometry. In this example, only one more root. For basic absorbance, this will be our ground state potential energy surface minima. We could also solve for even more roots if we wanted, and these will again just be single shot projections from the ground state geometry, and that's why I've shown them like this, because we don't know what's going on up there, we just know that's where the energy should be, roughly. This is also an approximation. There's a whole bunch of different approximations in this that I won't get into. We can also optimize for the excited state and do a vertical transition at that geometry to get fluorescence. When we calculate the oscillator strengths in our transition, what we're looking at is the orbital overlap between states. While this does come from the Frank-Condon principle, these are not necessarily a Frank-Condon spectrum. If we wanted to do that, we'd need to consider the Hessian in our calculations in order to do transitions from different vibronic states as well, which we can do using excited state dynamics, but that's beyond the scope of this presentation and costs a lot more. If we did calculate the Frank-Condon spectra, though, what we'd get is more realistic band shapes compared to our vertical excitations, which are essentially just spikes that have had Gaussians put around them to make them look a bit rounder. So These here are two very different molecules, just to clarify, but it sort of just gets the idea. The one on the right is from excited state dynamics, the one on the left is from just vertical transitions. But to what we actually do. So a vertical transition will occur from some point on the ground state potential energy surface to the excited state, and the variation in the placement on the potential energy surface gives rise to broad peaks. This is important when thinking about thermal contributions to spectra, and it's why we do need to consider all of these Frank Condon states when we do proper band shapes, which is not what we're doing. If the excited state is short-lived, the structure might not have time to relax and will emit a photon straight away. How boring. If the excited state is long-lived, the solvent and the solute will have time to relax before emitting, usually emitting a lower energy photon in the process. The difference between the absorbance and emission is the Stokes shift. And just to remind you, it's not as simple as this, but this is an approximation that we can use to try and understand it. This relaxation process gives rise to a particular feature of excited state solvation, that the solvent itself has two ways in which it can stabilize the solute with regards to the ground state. The first is the fast transition. So this is when the solvent gets polarized by the near instant electrical transition of the solute, but can't reorient itself in space in this time frame. And the second is the slow transition. So the solvent has time to reorient itself to better stabilize the solute. The terminology around these is where it starts to get confusing though, because in equilibrium solvation, the fast and slow responses are in equilibrium with each other, and in non-equilibrium, they are not in equilibrium with each other. So naturally, this means that we need to have some way to separate out these surface charges, and this maths here is really important and really cool, because what we're doing is using the refractive index of the solvent as the proportion of the whole dielectric constant that will be instantaneously polarized. Everything else will be slow and comes as a result of solvent orientation. Yeah, it's pretty much always around 2, but it does change slightly if you want to be very physically correct. Yeah, which I will touch on that in a couple of slides' time. So here, yeah. So here we separate the fast and slow component of the ground state surface charges. We polarize the fast component only with respect to the excited state of interest, and we sum the respective ground state slow and electrostatic fast charges, and excited state fast charges together. This process is really important because the slow charges will always come from the ground state, and the excited state will always come, and the fast charges will always come from the excited state in non-equilibrium solvation, and I'll touch on that in a second. To what Katya was saying though, here are some examples of some solvents. If we think about this for a minute, we can see what this actually means. Since all the solvents have a similar refractive index, low dielectric solvents will have a much greater fast component because they are dispersion-dominated species. So we can see in this case, hexane actually has a negative slow component. So yeah, anything where you're dealing with dispersion, you're dealing with a, not sure where that train of thought was going. The consequence of this equilibrium definition is 4 different conditions. One is ground state vertical transition calculation with the solvent in non-equilibrium, ground state geometry with the solvent in equilibrium, excited state geometry, solvent in non-equilibrium, and excited state with the solvent in equilibrium. I've described for a single excitation, but realistically, it's either going to be every state in equilibrium or every state in non-equilibrium. Going back to step 3, though, we see something really important. We cannot polarize the slow charges of the excited state directly. So instead, when we do emission, what we have to do is calculate the excited state in equilibrium and store the slow charges, which we can then use for the non-equilibrium calculation from the ground state as at the excited state geometry. This is really frustrating. But my recommendations on this are always do optimizations in equilibrium when optimizing for the excited state, Non-equilibrium should be used only for vertical transitions, and that is specifically for absorbance. If you're doing emission, you need a specific tool. It's a specific tool, so you need specific programs. Gaussian can do it, but it's really clunky to chain these jobs together. You have to manually specify, like saving out slow charges and then loading them back in. QChem can do it in a relatively easy manner, really poorly documented, but the examples on their website are not terrible. You just kind of have to trust that they're doing something that you think that they're doing. It's a big pain. NWChem does this really easily as a part of their VEM model, which I'll touch on VEM in a bit. But it's sort of a black box one-shot approach in that case. It just kind of does everything for you, but otherwise you can't seem to like extract just the slow charges and save them off. So state-specific versus linear response, the point where my brain gives up, the point where the slides get a bit verbose. I apologize in advance if I lose any of you here. This is recorded. Linear response solvation. This is different to linear response TD-DFT. This is how we calculate the solvent response to the transition itself. So in linear response solvation, at the core it uses the transition density to calculate the solvent response to the excitation. This is a product, though, of the linear response TD-DFT calculation and comes from the transition multipole moment, which means that it disappears for non-optically allowed transitions. This is a big problem. The solvent response in turn will be much smaller than expected in these cases, which, as I'm sure we all know, optically allowed transitions is not the definition for whether or not a transition will actually happen. So this can be problematic. This presents bigger issues where large electronic rearrangements happen, so charge transfer states, Rydberg states, things like that. In this case, there's actually really little orbital overlap between them because you are changing electron density so much. So you're not going to get a big transition density. State-specific theory instead uses the density of the reference state to calculate the slow charges, the density difference between the ground and excited state to calculate the fast charges, and practically speaking, this is computed by partitioning the reference state surface charges and repolarizing them in the presence of the transition state. So the key takeaway here, and this took a long time for me to get my head around because state-specific is such a frustrating terminology to use when dealing with excited states. This uses the difference in electron density between the ground state and the excited state of interest, the specific excited state, to calculate your fast charges. The slow charges will always come from the density of the ground state. Okay, so to break this down further, you take the ground state density, rho 0, to calculate the respective surface charges, sigma 0. You partition the surface charges using some partition function to get the fast and slow charges, which I've described here. It's the same as our chi from before. We perturb the fast component with the state-specific difference density to get our fast charges, and we recombine them to get the non-equilibrium charges. This is usually performed in one job. For emission, though, we perform an equilibrium excited state calculation, polarizing the charges against the excited state density. We partition the charges to get the fast and slow components. We perform a ground state non-equilibrium calculation, which forces the partitioning of the charges. So you're making sure that it does separate the fast and slow components, and then you're recombining them to get non-equilibrium charges. So note here, the excited state slow charges are coming from an equilibrium calculation as opposed to from a non-equilibrium calculation. So we can't just do a non-equilibrium vertical calculation from the ground state. So this typically requires two separate jobs to do properly. Like I said before, some packages will chain these together. My recommendations here are that linear response solvation is implemented in pretty much everything since it comes for free with vertical excitation calculation. If you don't specify what you're going to do in a program, it will either complain at you or probably just use linear response solvation. State-specific solvation is not implemented in most things, and in packages where it is not, most documentation is very ambiguous as to how it's handling the excitation. Every package that does linear response solvation will allow you to choose equilibrium or non-equilibrium. And this also means that linear response solvation can be used to calculate transitions between states as well. That should say that state-specific solvation can be used to calculate transitions between states as well. Remember that vertical transitions are a projection from the ground state to a higher state, so any errors will be propagated and exacerbated. The best linear response methods have errors of anywhere up to 0.8 EV in my benchmarking, which, to put that into perspective, if you're looking at a red photon, your error bar is the entire visible spectrum. So not great. Why this gets more confusing to study is that state-specific approaches can be considered as an extension or a correction to the linear response solvation approach. So the first state-specific implementation was called corrected linear response. The name has stuck despite these being very distinctly different approaches. And other excitation models use things like vertical excitation model, which makes it really difficult when you go to Google vertical excitation models and you get the vertical excitation model. It's difficult. When looking deeper, though, these models get even more confusing when you get into the territory of self-consistency with excited states. And one way to look at these approaches is to consider that their self-consistency in relation to ground state or excited state, similarly to how we can treat correlated method solvation. So here we can see we've got PTE, PTES, PTD, like we did before. In PTE, PCM solvation is self-consistent in the ground state before calculating vertical excitations as a non-self-consistent correction. We don't have an analogy for PTD here, but we have PTES instead, where we use PTE for the ground state before we also calculate before we're also going self-consistent in the excited state, and PTED, which is where we correct the ground state orbitals with the excited state surface charges and repeat until that's self-consistent. Under this model, we have some terms that become equivalent in the framework of TD-DFT, as I've sort of hinted at in my figure. So PTES is the same as VEM. Collected linear response is the first iteration of PTES, and PTED is also known as IBSF, or Improter, Baron, Schaumann, and Frisch. So it's very tricky and very case-specific, but also watch this space. There's more to come. Collected CLR and VEM seem to be the best approaches here. Paper suggests that IBSF, PTED are non-variational and change the ground state orbitals too much. So the TD-DFT calculation becomes less meaningful. And analytical gradients are more tricky because most of these are corrections, not analytical solutions. So SMD is still the best for ground state optimizations. For excited state corrected linear response seems to be better than linear response only in some cases, but is far more expensive. So this is where the field kind of breaks down, because there really isn't a huge amount. Simply put, we don't have many good options. Ground state dispersion corrections are not appropriate for the excited state since they're all parameterized. And ground state non-electrostatic terms are also not appropriate for the same reason. There can be large differences between the ground and excited state for geometry and thus for non-electrostatic solvation considerations. So the first model that we care about, though, is SMSSP, and this is the best one we have so far. Essentially, what we're doing here is Trullo, Kramer, and co. extended SMD to use the polarizability of the solvent as a scaling factor for the C6 term, using the refractive index of the solvent to get dispersion interactions, which you'll see that a lot in all of these methods. They wanted something that was pretty generally applicable, so they parameterized this on the average of a bunch of different functionals, though none of them were modern TD-DFT ones, so not the best in that regard. This does away with the CDS term from SMD and replaces it with a dispersion term which takes this form. As we can see, we've got a fitted term that scales the polarizability, and we use the refractive index as well. And we use this other parameterized term, which also takes from the surface tension of the solvent. So again, input parameters, very simple. The problem with this is that it requires us to manually calculate and input the polarizability of both the ground state and the excited state. Some other models that were used, essentially all I'm trying to get at here is that everything on this slide uses the same approach of refractive index to calculate some sort of dispersion correction, and everything on this slide takes a slightly different approach. So the first one, EFP, improved their approach, which could be useful in some ways, but in these other two approaches, they kind of decided that we need to use explicit solvent molecules to account for the fact that we don't have these non-electrostatic terms in place. So we need to explicitly calculate them through QM. This needs more work. It looks like room for a PhD. In the meantime, SMSSP is the best option, and it's available in NWChem. If you can get some of Vendetta Minucci's Gaussian modifications, I'd be interested to try them, but they only really run from Gaussian 3 and Gaussian 9, and who wants to do that? And as I said before, there seems to be a shift towards people giving up on including these terms and using explicit solvation and quite often quantum Monte Carlo or MD sampling as well, and it just gets too expensive at this point. Maybe EFP might be a better option. Yeah. Back to that time. General TD-DFT stuff is a bonus. Honestly, it's pretty simple. Always use a range-separated hybrid or range-separated double hybrid. These are pretty similar in behavior. BMK is a fluke in terms of how it responds. It was never designed to do anything like this, but it just happens to get good RMSD values. Yes, not so good for barrier heights. Still need more work in terms of investigating why it's good for excited states. Omega B97XD is great for ground state dispersion, but because it uses ground state dispersion, we don't really know why it works particularly well for excited states, but probably not the best for optimizing excited states. In terms of dispersion is present. Interesting. So there is the non-D version of it. So it might be worth investigating that as well. But in general, CAM-B3-LIP is my go-to for excited states only. It's reliable and numerically stable. Oh, cool. For range-separated double hybrids, these two are good and have been benchmarked. Basis sets seem to be not particularly significant. Diffuse functions are always needed. With how bad other errors are, just use 631G star. It's about as tight as we need. TDA, vital for triplet states. This is ignoring the B component of that eigenvalue problem. Also fails spectacularly for some species, so only use it for triplets. You usually need pretty tight grids because the TD-DFT calculation itself can be quite sensitive to that. And symmetry is a bad idea unless you know that your excited state has a particular symmetry, because the excitation tends to break your symmetry between the ground and excited states. You never know what your QM package is doing, so if in doubt, be explicit in your settings, especially for equilibrium. And many thanks go to everyone for listening, especially Sophie, Caleb, and Peter for putting up with me being in pain at my desk. To Katja, of course. Monash, ERC, and NCI. Sorry, I did use some of your guiding time, Peter. And check out our new website. Yay.